Hi, this is Brian Harrington with Mountain Sim. I'm going to be covering today our Automotive Simulation Guide, which picks up the pieces of the design phase and the operating and procedure phase and all the way to the continuous improvement phase, picking up performance metrics along the way. So really what we're looking at today is the complete manufacturing life cycle with respect to automotive procedures and design. So we'll start off with our design concepts. So we're going to be looking at when we're just in the phase of looking at a new Greenfield site, or which means a brand new facility or location has been established or identified, or a Brownfield site, which is where we have an existing facility, but we're going to be going in and doing some demolition and putting in a brand new facility into a building or plant that it currently exists. But either way, it is what we're bringing in a brand new design, new assets, new robots, new material handling systems. So our simulation, what we're going to find out, definitely becomes the prototype for this new manufacturing facility. Often in design concepts, we have the chance to actually have a prototype, to build a prototype before we start looking at a new product. And that design prototype very well could be even in the computer terms or an actual physical prototype. But our simulation model, when we put our concept and our actual layout and processes into action with an animation and packed full of statistics and data, that facility becomes alive in a sense, and we can conduct what-if analysis and sensitivity analysis. And the final goal is to achieve our marketing targets and iron out all the changes that might be required to achieve our targets prior to implementation. So in the design phase, this obviously is where engineers are going to be bringing in different concepts, different layouts, and we'll have usually a set of targets. So management might say that we need to come up with a facility that designs 60 vehicles per hour, and we have this allocated budget. So we have X amount of dollars to work with. And this is the area, the targeted area, location in the graphic location of where we're going to be designing this facility. So now we need to prove out these concepts. Are we going to achieve our throughput? Do we know? Are we going to design where the bottleneck or the constraint is going to be in the system? Do we know what line rates we're going to be running at various lines within the process? What are the effects of the downtime on the system? Is it going to cause us to not achieve our throughput? What particular material handling systems are we going to be using? Are we going to be incorporating power and free, electric monorail systems, power friction systems, even the material handling from AGVs to forklift to tugs and rack systems? These all are important facets of the design of the facility. And then along the way, when we're putting in all these assets and lines, how do we break up our synchronous behavior through decouplers and buffers? And when we're building subcomponents that have to meet key rendezvous within the facility, where do we broadcast these points to build that particular subcomponent to assure that it's going to make a robust rendezvous without causing any lengthy delays in the system? So these are all important design objectives. So now we can step into each one of the design objectives that are found within a typical simulation model. So obviously throughput really is the key metric when we're designing any manufacturing facility. What is our throughput going to be? So the plant might have and management might say we need to achieve at a minimum 68 jobs per hour or vehicles per hour in this facility. And this shows a runtime graph of throughput. And this very well could be placed in the X bar and R chart where we could see our control limits and we could see where the variation exists in an hourly throughput factor. And we could determine what caused some of these points to go out of control or achieve a low throughput, such as the point where we're looking at a jobs per hour that went below 36 jobs per hour. And we can see that these lines were set more than likely at a maximum line rate or a design rate of 73 jobs per hour. But the net average is just above the 68 target. So this very well could be displaying that we are achieving our targeted throughput of the facility. But the key here is, the key takeaway is definitely our throughput is usually the king metric when we are designing a facility. And as long as it can be implemented within the budget, that's where management is going to place a lot of weight, whether or not we're going to achieve that throughput. So when we do have a new facility, we know that in manufacturing, bottlenecks can come into the system. They could actually move around the system, and usually we can pinpoint a particular constraint in the overall process. So the constraint is the limiting factor. It's whatever throughput the constraint produces, this is going to be the throughput that's at the pay point of the facility. So it is it's often referred to as the weakest link in the system. So can we actually design where the constraint can be placed? Sure, we can. So we might want the constraint to be near the end of the facility, or if it's such where it's a very complex process within the overall layout, very well could be due to budgeting constraints and so on. It might be the constraint. So how do we go about protecting the constraint to make sure that it doesn't cause or minimize the low runners of that constraint? So if we know where the design or where the placement of the constraint, then we can provide protection around it. We might put some buffers in front of it or some buffers after it or some protective overspeed that is pushing parts into it. But we can design and place some techniques to protect and minimize the negative effects of the constraint. Now, if we don't have any clue of where this constraint is going to be, then you can easily see that we could be placing assets and protection in the wrong place, and that could be detrimental to our overall budget and achieving our targets. Now, bottlenecks can actually be a little bit more towards the second sector of what we talk about on operational procedures, because often bottlenecks can move around even from a weekly or monthly basis, or even within a day. Particular bottlenecks can occur. So we're gonna look at how we can, when we step into the operational procedures, how we can actually put some actions in place to minimize and protect when bottlenecks occur within the system. So the next important facet when we're designing a facility is obviously we're going to be stepping into the various line rates. We're going to have several lines and several stations and work cells that all need to work together, and they're going to have various line rates. They might not all have the exact same line rate. That might just run a facility with all the facilities running at a 60-second cycle time. We very well could want to have some of the upstream lines pushing into the next system. So designing, exploring and looking at the possibility of providing protective capacity in the eyes of a push system, so we can test these types of procedures out. We might want to look at whether or not, once we have various line rates achieved and looking at a particular run or what if analysis, look at what if in the future we need an extra jobs per hour. Can we get it with the current design that's in place? So we might want to protect for future market growth. And we also, very importantly, want to distinguish between manual operation and automated cycle times. We don't want our labor force to pace or drop or have losses in throughput due to shared resources or operators or forklift operators. So looking at the difference between manual and automated cycle times. And overall, we're looking at, are these lines set up to meet our market demand, and have we sufficient protection to, if the life cycle of this particular program is 3 to 4 years and we project some future growth, do we have does this plant protect for future market demand? So setting up line rates, very key to when we're coming to our design phase. Unfortunately, downtimes happen. So once we have these lines in place, we're going to experience mean time between failures and mean time to repairs. Just when a station goes down, we might have to we might have to lock out the entire line. So obviously, when downtimes occur, there's a great potential for overall throughput loss, and that could trickle down all the way to the pay point. So that could be one of the low points when we're looking at our throughput graph of when a particular hour has gone out of our control limits. So the length of the repair, how often it occurs, we might want to look at the number of maintenance resources we have, so we can put in our workforces such as millwrights and electricians, basically our maintenance crew, and we can actually even go as far as looking at the safety and lockout procedures. Like I had mentioned, if a particular station goes down, we can actually lock out the entire line. That could be picking up when a electrician comes out to a station and cuts off electricity for the entire line, and then locks out for safety protocol and goes in. So these all obviously add time to the amount of the overall repair. And nowadays, backup systems are very costly. We're not seeing that as much as we had in the past. So we're looking at these robust and bringing our system back up as quickly as possible. So when we're in the design concept, obviously moving material around the facility from marketplace to line side racks, very important. Overall, the overall facility itself, the actual vehicle that's getting built might be placed on within a palletized loop. And that pallet itself holds dimensional control information. So these pallets actually are expensive assets in themselves. A particular pallet might be near $20,000 with all its dimensional control to hold that particular component and vehicle in place so it can get welded spot on where it needs to be. So these in a facility, we might have near 300 pallets in the system. So that in itself is a multi-million-dollar question on how many pallets reside in an overall facility. We might have particular power-free conveyance systems that are delivering such body size or vehicle size to the overall body. We'll definitely usually have forklifts that are delivering material in tugs and carts, all the way to automated guided vehicles. Again, different systems that are delivering product from a marketplace all the way to some of the line side racks where the components are getting installed or assembled. So this is just an example of a power and free system. So in this particular example, we're showing the overall, it's an engine line. We're showing the overall main line where the vehicles are traveling down. And meanwhile, we have the subcomponent of the engine getting built up, and we have a power and free system. This is the loaded side, so the engines get loaded on a power and free. You can see that this represents an overhead power and free where the engines are hanging above the vehicles. And then they're going to get loaded at this particular point. And then we'll see our empty carrier return. So this can be nested within the overall manufacturing facility, or we might just hone in on this particular system and dial in the number of carriers in the system, how long should the empty return side be, and how long or how many engines are queuing up on the load side. And we can look at the overall system throughput, the jobs per hour. So very important as far as capturing various material handling systems. We can actually set this in motion here, and we can see that the engines are queuing up, and they're getting loaded at this particular point here, and our empty pallets are returning. And we can compare the overall throughput on this engine line to the overall throughput on the main line, or the cycle with respect to cycle times. And finally, looking at when we're designing system, obviously buffers and decouplers are very key to the overall design. So when we put all our stations together and we make up groupings for lines, when stations push into each other, we pick up synchronous behavior. Each one of these stations have its own respective availability. And when we start to multiply all these availabilities together to get an overall availability for a line, we can see that it doesn't take long before the overall availability starts to become an issue, a potential issue. This is where we break up some of the synchronous behavior through decouplers or buffers. And they could be just anywhere to 2 to 8 units, and that might be sufficient to break up some of the synchronous downtime behavior. So very key to when we're designing facilities. And also broadcast. It's a separate topic, but when we are building subcomponents, when do we want to broadcast to the subcomponent to build that particular subcomponent? So the timing usually takes place where it needs sufficient time to actually build the component, get it into the material handling system, such as power and free, and assure that it's going to make that rendezvous at that assembly point in time. And then sequence becomes important, because when you make a broadcast further downstream, obviously there's greater chance of the sequence to get the mainline sequence to get out of sequence or to have a late unit. So broadcast points, very key to the design. They can be become complex and very debatable because of the differences, and it's obviously more robust to sequence the earlier the closer to the actually sub-assembly, and it's more robust due to achieving that the subcomponent will be there the further downstream. In this example, we have it such where we're sending the broadcast point early in the system here. So this represents where we send the broadcast. This is the subcomponent right here. This represents a body side, and we're actually receiving the signal. So this information says it's this type of vehicle. It might be a vehicle type 1 or a vehicle type 2 or a vehicle type 3, and it's going to build that respective vehicle type, place it into the power and free system. So we see that this is the loaded body side or vehicle side that's traveling to a particular point or rendezvous point where it's going to meet the main line and take that subassembly. And then the empty carrier returns on the empty return side. Now, with respect to sequence, if we can see that this was sent early on, that gives us a better chance for the body sides to actually queue up and be present. So, but we have a greater chance of the sequence possibly getting out of order if one of these vehicles went through repair spur or a parallel line and got out of sequence, then we could have a potential issue. So often the broadcast point, if it's closer to the actual build, you have less opportunity for the overall sequence to get to stay within sequence. So very key to design concepts. And into the operational decision or the operational procedures phase. And this is where once we have implemented our design and we've got the plant actually launched and up and running, often we're going to be looking at what's the best way to actually run this plant. You know, we can step into looking at the shift patterns and different operating rules. So this is where we're going to be spending a little bit of time looking at some of the operational decisions. So operational procedures, like I stated, is once the facility has been launched, we're up and running, we're going to often see quite a few different, our objectives, our overall set of objectives might shift a little bit towards looking at how our market demand, when it fluctuates. So we might say that if we were building some convertibles, once summertime approaches, we're going to be seeing on our facility that we're going to be possibly running more convertibles, and so we'll have some differences in our take rates. So this definitely touches on the mixed model assemblies. So we're going to see that more than likely this facility is going to be running different vehicle types down the same assembly lines. You know, exercising flexible manufacturing. So we might be producing 2, 3, or 4 different vehicle types. And so obviously there's going to be some operational and different release rules of building a set of, or the mix of vehicles and the release patterns on how we do that. Even just looking at the shift patterns in labor itself. So touching on when we have morning breaks, lunch breaks, afternoon breaks, so the operating patterns. And once we have the facility up and running, we know that bottlenecks can occur, and the bottlenecks can actually move around the system. So how can we protect and get procedures in place to minimize the effects of bottlenecks? So let's go ahead and step into looking at some of these objectives. And before we do, we'll look at an online, this was from the Ford Motor Company's online magazine, and it just shows by 2017, which we're currently at, that Ford on average is producing 4 different vehicle types in each one of its facilities. So the days of just building 1 vehicle type per plant is pretty much in the past. So now we have less overall manufacturing facilities, yet our family of products might be even growing. And so we're definitely using the flexible manufacturing and the mixed model assemblies, and we're doing more with less. So our facilities are becoming more complicated, yet we're able to pull off building, we could be building a sedan and a pickup truck, for instance, on the same platform. And we very well could be looking at this facility running 2 to 3 shifts. So the wiggle room of producing lost units via overtime is definitely minimized. So it really puts the pressure on when we're trying to meet our targets to get it done within the allocated shifts, because we very well could be running, like I say, close to 24 hours or full shifts or full capacity at that particular plant. So when we look at how simulation can improve our key operational objectives, we're going to be looking at this facet of mixed model assembly, building several different vehicles down the same assembly line or through flexible manufacturing. Often it touches upon our actual build schedule. So are we going to batch build? Are we going to be building to order? And often it is a combination of the two. So optimal operating shift patterns is key also, and optimizing the staffing requirements and utilization. So when we look at optimizing for mixed model assembly, we're building different vehicle types on the same line. So in this particular instance, we might, within the model, have 4 different vehicle types. In this case, we're using a probability profile distribution. We have 28% of vehicle type 1, 34% of vehicle type 2. We have a low runner, 9% of this vehicle type 3, and finally 29% of vehicle type 4. So when we do that, that obviously increases our overall complexity of the facility. And we might have unique dimensional control equipment on each one of these platforms. So when we talked about a palletized loop, are they going to be, can these vehicles all be produced on the same platform or the same pallet? And the answer might be yes, or this low runner might require its own unique pallet. So that complexity in itself becomes large on just managing unique pallets within a palletized loop. It can become very complex, particularly if we're building to a customer order. And each one of these vehicle types might have unique cycle times. So, we talked about in the design phase coming up with optimal line rates and station work cell rates, and balancing manual and automated operator, or manual and automated cycle times. How is that going to affect us when we're looking at each one of these vehicle types having a unique set of cycle times for both automated and manual? So the vehicle sequencing and scheduling obviously becomes very key to the overall performance of the system. And when we have additional vehicles in our family of products, this is definitely going to increase the overall line side racks that are key for our sub-assemblies. So when we look at a set of vehicles, in this example, we have 3 different vehicle types, and not all like we just discussed, not all vehicle types are equal. They're going to have different cycle times, require different subcomponents. So scheduling is very important and requires usually quite a few different what-if scenarios. So what is the best build schedule? Often we try to build to a customer order, keep it close to the customer order as possible. And if we have a low runner, maybe vehicle 2 has a much, requires a greater cycle time. That could cause potential throughput losses for vehicle 1 and 3. In other words, vehicle 2 would be pacing the line. So we might want to test out, if we do have a low runner, maybe possibly building that in small batches is going to be the best, or possibly coming up with some blend of vehicles, or potentially just different release rules. In other words, we might say never release more than 5 of our low runners in a row. So coming up with different scheduling rules often becomes a very, very complicated without a simulation. If you were trying to do this deterministically, it's going to peter out very quickly. So in the simulation world, we can really test out various build schedule patterns and sequence and look at our overall sequence, and we can come up with what is the most optimal release pattern that comes that gets us close enough to our original customer order, but also achieves our overall throughput targets. So once we do have the facility up and running, and we're achieving and we're looking at achieving our overall throughput targets, we want to look at our operating patterns. Are we going to be running this facility within 8 hours? Are we going to be looking at 10-hour shifts? Are we going to be releasing our operating force with a tag versus a mass release pattern? A tag situation might say if a particular operator is going on break, then another operator comes in and continues where he left off, with where he or she left off. So we're going to continue the operation. In other words, there's really no stoppage. Where a mass relief pattern, all operators, or at least a subset of the operators, will go on break at a particular point in time, and the facility will actually go down for those, maybe 10 minutes or for 20 minutes for its lunch time. So coming up with the optimal operating pattern, and even staggering different shift or break patterns within the facility that causes the minimal throughput losses when we're looking at an overall shift period. So that brings us to the actual detail of when we do have our operators placed in the various lines where they'll be working, looking at coming up with do we have a sufficient labor force in place? Can we find out where the sensitive areas in the system are? And what are we going to do to protect these sensitive areas? So are we staffed properly to handle our downtimes? Do we have our skilled trades and maintenance plans in place? Do we have sufficient material handling operators such as forklifts and tug drivers? Do we have our marketplace where parts are coming in or in subcomponents? And are they getting delivered in key time for those line side racks? So looking at our operators becomes key when we're trying to keep our facility up and running. So once we have our procedures in place, and we're trying to keep them to achieving our targets. So this comes to basically the old saying is, if you can measure it, you can manage it. So of course, good designs such as poke-yoke design airproofing procedures are going to keep us to achieving our targets. But continuous improving and having a set of performance metrics in place is going to be give us the tools to make sure that when we start to lose throughput or have potential, when we're looking at our control chart, when we see that we are actually experiencing some low throughput hours and so on, how can we minimize those? So when we come up with a set of performance metrics, and this will be our next topic that we're going to cover, and that'll tie into our continuous improvement and tracking performance metrics along the way. Now we're going to be looking at our last phase of our automotive simulation guide, which steps into the continuous improvement and performance metrics. So this is an important topic, particularly when we're looking at a set of performance metrics. This is going to give us the tools that we require to continuously achieve our, try to continuously achieve our targets and create improvements along the way. So continual improvements and starts with the concept. If you can measure it, you can manage it. So most of our plants are going to have systems in place that collect a lot of real-time shop floor metrics, and that could be our overall working and waiting and blocked and downtime. So there'll be a lot of data that'll be coming at us, and when we take this data and we can actually come up with a set of performance metrics, and that could include our quality, our scrap, our availability. So we'll look at various common metrics that are used within manufacturing facilities. So once we have these metrics in place, this is how we can come up with the improvement plans that lead us into the continuous improvement. So what should we be measuring? And these are some of the most common. We talked about in our two other sectors of design and operational procedures, the jobs per hour or vehicles per hour. Obviously keeping our eyes on that is key. Our financial costs, that's particularly important in our design phase when we're purchasing assets, but it's also within our overall operating procedures. Are we still achieving our costs and our return on investment on particular assets? Our first pass yield, that looks at quality, that looks at the effects of scrap and rework items. Overall equipment effectiveness, OEE, that picks up the facets of availability, performance, and quality. And then our schedule adherence, our late units within the sequence causing us problems with meeting our customer order or order to delivery. How long does it take us to design a particular vehicle? That's often referred to as dock to dock or the overall time and system. And of course, our resource utilization. How are we utilizing our assets or our operators in a fair fashion, achieving possibly 80% utilization? Are they balanced, in other words? So jobs per hour, we looked at this earlier, and this was our example. Simulation always provides us a nice runtime chart of our overall throughput, and often this is one of the metrics that we're going to be looking at, and we can pinpoint when particular points fall out of our control limits of saying that 36 jobs per hour is an issue. And what caused that? So we can go in there into the model and find out exactly what caused this. Was it a set of simultaneous events that occurred? Was it one particular event that caused this? And can we minimize it? What can we do? Or what do we have to do to react to repair this? So the time to react to a particular event that caused us some sufficient throughput loss. So in this case, it might not be catastrophic, but if we ran this and found out some catastrophic downtime that occurred us a real lengthy stay here, what are we going to do to protect that? So our overall throughput, often it's a good idea to graph and chart your metrics. So when you get a column of data, first thing you want to do is always put it in a graph form and get as many statistics as we can on it. So we take our graph or our data, and we can create different charts. Often throughput comes into a beta distribution where we have some tail that is our low runners and some maximum, which is our design rate, that is its capability that it can do, at its best that it can do. And then we're going to see our average throughput. And this usually can be just easily captured within just three simulation objects, just a simple buffer that holds at our pay point, that holds units for 60 minutes, then pulls them out at 0 cycle time. And the actual work complete metric actually even keeps track of our time in system as well, which is another metric. But particularly right here, we're looking at our throughput. So the Simulate has a nice built-in feature for keeping track of our some of our financial metrics. In this particular instance, we can actually have a capital cost and then put the usage cost per time unit in, and the usage cost per unit. So we can actually look at our return. When are we going to achieve our return on investment, particularly on obviously on expensive assets. So each one of our line might have some of these financial metrics that are particularly key when we're close to when we're in our design phase in our operational procedures, keeping our eye on the overall profit of the system. First pass yield. So this is switching gears over to a little bit of our quality side. So first pass yield is a good metric that just keeps track of the number of parts that have passed through a particular workstation, and we're going to keep track of how many of them were good, whether or not one of them was, or the number of them that were scrapped, and also the number that actually were reworked. And so basically we're finding out the parts that were actually good minus the ones that had to be reworked or scrapped, divided by the total number of parts. And this gives us a percentage of the first pass yield, which really represents the number of good units that have passed through the very first time. They didn't need to take a second pass or a third pass due to quality issues, or they ultimately were not scrapped. So obviously the goal here is to minimize waste with respect to scrap and rework, because rework obviously takes time, and it's going to possibly reduce our overall throughput. Overall equipment effectiveness. This is a pretty key metric in the sense that it does pick up our availability, our performance, and our quality. So when we're looking at overall equipment effectiveness, we're basically looking at the overall operating time. So this shows us the full window of time that is potentially there for us to build units. But when we add planned downtime into the overall picture, that represents morning breaks, lunch, afternoon breaks. So we know that there's going to be planned downtime that's going to reduce that overall time to build units. So that's going to be, so now our window is becoming smaller. We know that downtime exists. So when a line experiences mean time between failures and mean time to repair, downtimes occur. So that actually is now reducing our window of operating time even smaller, because once we come up with those figures, they're going to occur. They might be random, stochastic in nature, but they do occur. We know that once we have facilities designed and lines operating with each other, they cause weights and blocks. That is usually what we refer to performance loss, or when a system goes down, it has to start back up. So it might have a little bit of a ramp up time to achieve its optimal line rate. So performance loss particularly comes into play when we're looking at our weights and blocks. So again, our net operating time now, the overall window to actually build units is becoming smaller. Then if we look at quality portion of it, quality could be some of our reworked units take longer, scrap losses, so the part actually is just scrapped and just thrown out of the system. So again, that's chipping into our overall productive time. So now we just have to actually this small amount of time, or relative to where we started off, to actually build units. So overall equipment effectiveness, very key metric, because it does look at our downtime. It does look at how these systems are performing with one another as far as weights and blocks and performance losses, and it keeps track of our quality. So key metric, easy to track within discrete event simulation, and often this is closely related to our working time. That simulation picks up automatic for us, multiplied by the actual quality loss. Schedule adherence percent. So often this is due to late units in the system. So if a particular vehicle got out of sequence or had to go through a parallel line that was running slower, but for some reason it got out of sequence. So typical causes for late units: repair loops, parallel lines, quality tests, sometimes the couplers with shortcuts. So if a vehicle goes into a buffer, and there's various ways that it can actually get released out of that buffer, such as overhead mezzanines or large storage banks, often parts can get out of sequence there. In some cases, like an early unit, that might not be a problem within our sequence, but usually late units are a problem. So schedule adherence is really a simple metric in the sense that it's the actual production divided by the scheduled production times 100 is going to give us that percent. So often in manufacturing, like I say, late units can cause issues. Early units usually aren't too much of a concern. So our next metric that's key is this overall time and system. So how long does it take us to actually build a vehicle? Sometimes it's referred to dock to dock, referring to the loading dock where raw materials come into the facility, all the way out to our pay point or our shipping point. So sometimes we might actually pick up a control part, and that says, that we're not actually going all the way to some of our raw material, but the control part might be, let's say, where the vehicle the body gets placed on the pallet. We want to know once it's placed on the pallet, and it is now flowing through our body shop, and then we'll keep track of it all the way to where it gets sent off to the paint shop. So various different points where we can measure time and system. And if we have some of the units that are taking longer than others, they could be causing potential bottlenecks. And these bottlenecks could actually move around within the system. So rework items, shift patterns, different product variants, waiting on line side inventory. All these things can affect our dock-to-dock or our time and system. So resource utilization, we always want to keep our eye on our resources. We usually don't want to have our assets and our robots, all our expensive manufacturing equipment waiting due to an operator or waiting due to line side material getting delivered. So keeping track of our utilization and looking at if we have some operators that are operating, maybe we have above 80%, maybe that is going to be too sensitive or risky for us. So we might want to, at that point, rebalance some of our line operators. So if we have shifts in our production schedule, is that affecting our operators? And do we have them and all their tasks balanced correctly, so we can assure that we're not going to be that a particular operator is not pacing the line. And that comes into play from our operators that are actually building the product to all the way to our maintenance crew. So a little bit close up on some of the metrics that we discussed. If in our body shop model, if I zero it in on just like a particular line like line 15, this is a good example where this actually is a particular line that has a weld inspect. So every so often a vehicle might get pulled off just to inspect the welds and then get reintroduced into the line. So in this particular, it shows a buffer. This possibly might be 8 units. So we have a buffer here of 8 units. The units even here might get out of sequence unless we force them to maintain sequence, because they might take a shortcut or they might travel the full length. So there's quite a few different concepts or potential areas where sequence can get out of sequence, or a late unit, due to a buffer or due to the inspect. But each one of our lines, here's the example of how we can keep track of these metrics. So we can look at the jobs per hour at this particular line, or the overall facility. So in this instance, it was at 48.8. We could be keeping track of our financial costs along the way. So for running it for X amount of time, this might have been a 3-month run or a half a year run, whatever it might be for our runtime. And this would show our potential profit for the facility, or even for this particular line. Our first pass yield. So we learned that vehicles that get flagged for quality issues, such as scrap or rework, is going to impact our first pass yield. In this case, we're showing a first pass yield of 97%. Our overall equipment effectiveness, that is our availability, which is this line might be running at 96% availability. It might have the performance of 85%. So that's picks up our weight and block together. And so an overall of 85% as far as performance. And then so it could be showing 3% rework. So that is 97% quality. You can see that the overall OEE would be just below 0.8 when we multiply all 3 of those factors together. Schedule adherence, this is just looking at the number of units that have passed through the system that were on time. So it looks like we're 83.7% of the meeting our overall schedule, and we are getting 1,325 units that were deemed late or out of sequence. The timing system, or the dock, we're showing an average of 299 minutes in the system. And this particular asset right here might have an overall availability of 87, might be deemed as high, and 2% travel, so traveling between the line 15 and the inspect if he's actually doing that shared task. Okay, so that covered some of our basic performance metrics that we put in place to achieve our targets while we're running a facility. And often these metrics are discussed in weekly quality meetings that the plant might have. And these meetings are where we come up with concepts for implementing continuous improvements and how we run this plant and to achieve our targeted throughputs, and also how we go about implementing continuous improvements. So at this time, we've covered all 3 facets of the design phase, all the way through operational procedures, and finished up with continuous improvements and tracking performance metrics.